Hello, you are most welcome, ladies and gentlemen, to Real Impartation Moment on Tuesday Night Anatomy with Daniel Open. Today's section, we continue our series regarding the myology that we've already begun. So my friends, if you've not watched the previous, first part video on it, kindly get a video link and watch it. Because importantly, for you to understand, the subsequent, sections that we are going to have, then you have to really understand what we've done already. Okay. Now today, the reason is that today I'm going to begin with, the mechanisms, okay, involved in muscle contraction. And you have to understand some proteins which I made mention in, of course, the previous video, for instance. Okay. So that is what we are going to do. We are going to go a little bit, longer so that I can explain a lot of the concepts, for you. And so, without much ado, let's set the ball rolling. So, the first thing we want to tackle today is to look at, the mechanism of striated muscle contraction. We want to look at that. The mechanism of striated muscle contraction. That kind of contraction and relaxation cycle we want to understand, okay? So, the first thing is what we call, this concept is something we call the sliding filament model. Sliding. Okay, the sliding filament model. That's the concept we want to explain, okay, for you. Now, the last time I told you that some important myofilaments, which will be very useful as far as the contraction and relaxation of the muscle, okay, is concerned. I made mention to you, we talked about actin, and then we talked about the myosin. Now, the first concept I want you to be aware is that for muscle contraction, okay, to be evident, okay, it's taking place at that molecular level where we have those proteins interacting. Now, the first thing I want you to know is that actin has an area where the myosin is supposed to interact with. Now, whenever I'm talking about myosin, I'm interested in an area of the myosin. The head of the myosin is supposed to interact over there. And whenever there's that interaction and it becomes very strong, then we see muscle contraction. Okay? When, of course, this kind of bridge, which is formed between, of course, the actin and the myosin, okay, head, is dislodged, then, of course, relaxation, takes place. So we are going to understand how this concept takes place in striated muscle. After that, I'll take you through that which happens in, of course, the smooth muscle, the visceral muscles. We want to understand that one too. So this concept, okay, where the striated muscle contraction and relaxation is going to take place is what we call the sliding filament model. Okay, the widely accepted, concept that we want to look at. Now, the last time too, I told you that there were some other proteins which were associated with actin. My friends, understand this concept for me. There were some other proteins which were associated with actin, and those proteins, we call them regulatory proteins. Now, because they will be associated with actin, they are going to regulate, okay, the nature of the active site, whether there's going to be vacancy for the myosin head to interact or not. Okay, that's also another principle. So what were these regulatory proteins? We made mention of two proteins. Say we have something called troponin, and then also we have tropomyosin. So we have troponin, and of course we have tropomyosin. Now, the first thing I want you to be aware is that the tropomyosin is the one which wants to hinder, so to speak, the myosin head for interacting with the actin at its active site. In other words, at the active site of actin, finding itself over there, if there's no muscle contraction, then what is happening is that we have what we call tropomyosin. Tropomyosin. Okay? It means that one will be very important in inhibiting, okay, the interaction between actin and myosin, so that no muscle contraction will take place. Meanwhile, we have another protein, which is the troponin. My friends, the troponin will have three areas that we have to be aware of. There's one area which we call it troponin I. Okay, so I for inhibitory. Troponin I. In other words, if tropomyosin and troponin I, they interact, okay, or they are working in unison, or they are working in synergy, then it will ensure that no muscle contraction will take place. But there's another area which we call it troponin C. My friends, troponin C. Now the C over there is for calcium ions. Okay, so it means that it has an area which we are calling troponin C for interacting with calcium. So we are going to see that this muscle contraction, whether it's a striated muscle or smooth muscle, will be calcium ion dependent. Yes, will be calcium ion dependent. We need calcium ions, okay? And that is why I told you that in the one important organelle of course, the muscle cell, which I told you is, of course, the sarcoplasmic reticulum in the sarcoplasm, okay, is going to be well endowed with, of course, this kind of calcium ions. It's going to store the calcium ions. So that when we need them for muscle contraction, I told you that there were some kind of area dilatations, areas, okay, of these sarcoplasmic reticula that we call them cystini. I'm interested in the terminal cystini so that they can, of course, bring out these kind of ions, okay, through the, of course, the transverse tube will go in there, and of course, for this contraction to take place. We are going to see that. We will see that for the smooth muscle, we have some other area which we call it caveoli. We will explain all those ones, okay, for you, which can, of course, be likened to, of course, this kind of smooth endoplasmic reticulum, the cystini that we have over there. Okay, so it means we need calcium ions. That's another point. So it means calcium also interacts with this protein, which we are calling it, troponin. So troponin C will interact with the calcium. Now, once troponin C interacts with calcium, okay, this troponin now becomes energized. Now, this troponin also has another site for interacting with tropomyosin, which I told you it is what, inhibitory, because it's going to, occlude the binding site for actin, for myosin on actin. Okay, so once that happens, okay, once calcium interacts, okay, there's calcium, okay, at troponin C, then what will happen is that this troponin will become, energized so that it can push away this tropomyosin away, so that there will be a free area for troponin head to interact. So that is exactly what we want to explain over here, the sliding filament model for you. So please just understand this concept. It is pretty simple. Okay, so the first thing we want to say is that we will have this protein, and this protein we are talking about, so let me call it okay, so the protein I am interested in is this guy, which we are calling it myosin. Okay, so the first thing we want you to be aware is that I have this protein, which is my myosin. And as you can clearly see, I can see some hairs. Okay, so I have the myosin. I'm not interested in the tail, I'm interested in the head. Okay, so we have myosin head. Okay, that's one useful thing that I want you to be aware of. Now, this myosin head, in its resting state, so to speak, okay, where it is not firing, where it is not interacting with the active site on actin, okay, what we see is that it will interact with some proteins. Sorry, it will interact with some molecule. I'm talking about the energy currency of the cell, ATP. Okay, ATP. So I have ATP interacting with, of course, the myosin. Okay, so that is one thing that we want you to be aware of. Now, the interesting thing over here is that I'm saying that the proteins, which proteins are you talking about? We've seen myosin, then it means that there will also be actin. Now, just schematically, but one thing that we are interested in is that we are going to see that this actin okay, so assuming these are the active sites for actin, I've told you that there will be other things which will be associated with it, which will be occluding. Let me use a different color, and those occluding things, okay, at the active site, so to speak. Let me put these black things in here. And what am I talking about? These black things, I'm talking about tropomyosin. So assuming I have actin and these proteins tropomyosin, which is occluding the binding sites, okay, for myosin. Okay, so that is what we see. Now I told you that it is not only this tropomyosin which is present, but also we also have some other proteins. Some other proteins are also present. And which proteins are we talking about? We are talking about troponin. Already, I've told you that for the troponin, we have troponin I, or let me call this one, okay, troponin I. Then there will be another one which will be interacting with this tropomyosin, which I call the troponin T. And then we also have another one which will be interacting with calcium, okay, which we will be calling the troponin C. Okay, that is what we want to see. Okay, so good. So that is what we see. Now the first thing that I want you to be aware is that this troponin that we have over here, okay, so this myosin we have over here, okay, now ATP is with it. Now the first thing that is going to happen is that the myosin hairs over here, they have ATPase activity. Yes, the myosin hairs are able to cause hydrolysis of ATP. Now, so there's going to be something we call hydrolysis of ATP. Now, whenever hydrolysis of ATP happens, so I'm going to say something that the next thing that is going to happen is that now there's interaction, nothing is happening, no firing. Now, the next thing for us to see is going to be hydrolysis. Let me put it here, hydrolysis of ATP will take place. My friends, we know that whenever there's hydrolysis of ATP, energy is released to drive certain processes. So that this time around, what we are going to see is that after hydrolysis of ATP, assuming I still want to place this one here. Yes, I mean, this one will be, let me say it's a boost. The new one is going to be reorientation. Now, after hydrolysis of ATP, there is something we call reorientation. So what we say is that the myosin hair, after hydrolysis, it goes forward. It goes forward. Now, it has moved from this point to this area. So it cocks forward. And literature tells us that the distance from its original position to another point is just about 5 nanometers. So it cocks forward. Okay, that is what we see. Still, we are going to see that area which will be interacting with it by way of having ADP, okay, because after hydrolysis we get an inorganic phosphate around too. So ADP and an inorganic phosphate. So that is what is going to happen. Now, so one point that we want you to be aware is that whenever there's hydrolysis of ATP by the myosin hairs, the myosin gets reoriented and also it gets energized. Yes, that's what is going to happen. So now it is energized so that it can cock forward. There's reorientation, cocking forward about 5 nanometer distance from its original position. Now once it cocks forward, so we see something over here. Then there's the need for a signal. Now this is where I want to tell you something. That yes, we've learned about we are talking about muscles. Muscles are effector organs, just like glands. Glands will secrete, muscles will contract. So there will be some kind of nerves which will interact with these muscles. And you know them, of course, by way of motor nerves. So you have the motor nerve, okay, so that its axonal terminal, there will be some kind of vesicles in there storing some important transmitters. And I'm interested in acetylcholine. So acetylcholine will be released, okay, once there's a docking, okay, so this, vesicle will dock with the plasma membrane of this, axonal terminal, so that it can what? Release its neurotransmitter. Yes. And this kind of area, the synapse, the point between, of course, this motor, nerve, and of course, or this motor neuron, and of course, this effector organ by way of the muscle cell, is the one we are going to call the neuromuscular junction. Neuromuscular junction. I'm sure you are aware that acetylcholine, there are two main kinds of receptors. We have muscarinic receptors. That one is for the secretion, the glands will bear them. Now, for the muscles, at the neuromuscular junction, the synapse over there, which we can also call the motor end plates, okay, those receptors over there, we call them nicotinic receptors, so that they can interact, okay, over there. And the important thing is that once this happens, there's going to be influx. So calcium will move, okay, into this time around. We are releasing that calcium from where? From the sarcoplasmic reticulum, or from the cisternae. Okay, so from there, from the sarcoplasmic reticulum of the sarcoplasm, what do we see? Calcium is going to interact with who? This time we're going to interact with, so we are going to have calcium interacting with this. Okay, so calcium ions interacting with, of course, troponin. And once there's that one, then what happens? This troponin will get energized, so to speak. So that what will happen is that the interaction point with troponin, it will interact with it and it will push these kind of troponin molecules away from the binding site. So what we are going to see is that these troponin molecules, okay, are going to push the tropomyosin. So let's say they will try to push them away so that they may move away from here, from the binding site. So that the site now becomes free for who to bind. The myosin has to now interact, okay, with so these areas are free, so that there will be that kind of interaction between the myosin hairs and, of course, the actin at its binding site. But my friends, is that all? Now, this kind of interaction is going to be a weak interaction. Why? Because we see that still ATP and inorganic phosphates, they are still binding to the active to the myosin head. So the interaction, which in this case we are calling it cross bridge, okay, is formed. But this one is a weak interaction, a weak cross bridge. Now the next thing that's going to happen is that, yes, these kind of, inorganic phosphates will be released first. So the first one to be released is going to be the inorganic phosphates. It will go out. Okay, and then the next one where is going to take place will be the ADP, will also leave. So that now the myosin head is now free. So that it can really interact in there, it can even go to the deeper region of this myosin, so that it can interact with the myosin. And that is what we mean by the power stroke. Power stroke. So power stroke is that avid interaction, okay, between, of course, the myosin hairs and the active sites in the inner region of course, the myosin, where the myosin molecules are. Okay, so that is as simple as that. That is what we call the muscle contraction. So what we are saying is that these hairs, they've interacted over here. There's power stroke. Okay, so it means that what is going to happen is that contraction will go on as long as the myosin head, is in contact with, of course, the active site of the actin. Okay, so that is what we are going to see. Now, the only time where there's going to be that break, that dissociation of course, that cross bridge is when we are going to see what you call it, the interaction of ATP molecules, okay, interacting with, of course, the myosin again. That is the only time the firing, the contraction will cease. Why? Because there's going to be that kind of dislodging of course, the hairs of myosin with actin. Okay, so it's as simple as that. Okay, the concept is pretty simple. What are we saying? We say initially we are going to have, of course, the myosin head, which is in a state where it is not having a lot of energy. Yes, because hydrolysis has not taken place. ATP is bound to it, but hydrolysis has not taken place. That's the first thing. And then number two, its orientation. It hasn't positioned itself so well to interact with actin. Okay? But what happens is that this same myosin head is having ATP's activity, which means it's capable of hydrolyzing the ATP molecule. So upon hydrolysis, then what will happen is that it's going to cock forward. It's going to get reoriented. There's going to be a conformational change. Okay? It's going to be, get energized, so to speak. Why? Because there has been hydrolysis. Okay, that's the energy carriers of the cell. Once there's hydrolysis, that takes place. And that cocking, moving a bit forward, is about 5 nanometer, okay, distance. And then still, I'm saying that upon hydrolysis, we get ADP and we get an inorganic phosphate. They will still be interacting with the head, which means that, yes, it's still not very free, so to speak. Okay, it's still not very, still having some kind of attachment, so to speak. And so its interaction, okay, which I told you that at almost the same time, there's going to be something we call, the motor end plates at the neuromuscular junction. Okay, the motor nerve is going to release, of course, the neurotransmitter in the vesicles, okay, after docking with the membrane, releasing it into the motor end plate or the neuromuscular junction. There will be receptors on this muscle cell that we are talking about. And what receptors are they? They are the nicotinic receptors for who? Acetylcholine. And when that happens, yes, it causes calcium ions to be released from where? The sarcoplasmic reticulum. Releasing them so that this time around the calcium knows where it is going. It's going to interact with the troponin component, which are called the troponin C. And troponin C, upon getting interaction with calcium, then what is going to happen? It's going to also get re-energized. Now it's aware that I have to do something. Now this tropomyosin is occluding the active sites for the myosin head to interact. So what is going to happen? The troponin will push away what we are going to see, this kind of tropomyosin molecules, so that we have free area for the myosin heads to interact. But still, ADP and inorganic phosphate, they are still interacting. So that connection is not going to be avid. It's not going to be strong. It's going to be a weak interaction. But with time, what is going to happen is that the inorganic phosphate will be released, okay, so that ADP also be released. When that happens, what we are going to see is that it's now free, so that it can really bind, go in there, and that is what we call power stroke. It can really go in there to interact with the deeper areas where we have the, actin molecules. Okay, now that interaction, that weak interaction, we formed a cross bridge. Simple. Now, it is only and only when we have no ATP molecules interacting with, of course, the myosin that, of course, firing will cease. We will dislodge the bridge, the cross bridge. Yes, that is pretty simple. Okay. Now, this is where one important concept comes here. And I don't know if you've seen someone who is dead before. Okay. You've monitored a dead person. Okay, from the time of death up to about 24 hours, you see that something happens, especially with the limbs. You see rigidity. They become so rigid with time, not instantaneously with time. After 2 hours, 4 hours, yes, that's what we see. Something we call rigor mortis. Rigor mortis. One of those physiological events that take place after death. Rigor mortis. Rigor mortis. Now, rigor has to do with rigidity, and mortis has to do with the dead. Humus has to do with the dead. So, rigor mortis, that rigidity. Why? Because with time, after 2 hours, 3 hours, yes, humus. Okay, postmortem states. What we are going to see is that what is happening? Various metabolic processes which generates ATP. they go down. Yes, I mean, essentially, they don't happen again because you are dead. Blood is not flowing. They are not receiving the oxygen. They are not receiving the nutrients via the glucose to generate ATP molecules. So what is going to happen? Your ATP store will go down. Once the ATP stores go down, then what are you going to see? You see that this, once we have the last ATPs there, which have interacted with, what do you call it, the active site on actin, then it's going to stay there. Because you don't have new ATP molecules coming in to dislodge that binding, then it will still be avidly present. That's why, especially for the limbs, upper limb, lower limb, you see that rigidity after that, okay, after some time. That is what you call rigor mortis. Rigor mortis. Good. So that is with the sliding filament model of striated muscle. I have to be very quick and tell you something about the muscle contraction in smooth muscles. Muscle contractions in smooth muscles. Yes. For that one, I want to tell you something. In smooth muscles, we don't have the regulatory proteins related with the actin. So we don't have troponin, neither do we have tropomyosin. That's the first point. Okay? Now, the next thing that I want you to also be aware is that in that one too, we don't have the myosin hairs having ATPase activity. Yes, another point. So let me explain that one to you. The first thing that we need, okay, regarding okay, so the first thing that we need regarding this contraction, again, is that these contractions we are talking about, okay, they are calcium ion dependent. Yes. Again, we need ATP molecules. We need to hydrolyze ATP molecules. So that one, I mean, there's no doubt over there. But what I'm trying to say is that the myosin hairs, in the case of the smooth muscles, they don't have ATPase activity. I mean, studies have not shown that. But then, what do we see? This is what I want you to sketch in there for now. Now, for the smooth muscle, last time we got to know that they were spindle shaped. Or we say they were fusiform. Okay, that's how they look like. With also an elongated look like in there. Now, one thing that we see for the smooth muscle is that we will see some things which resemble the actin filaments. Yes. Which resemble what we call the Z-disc that we had in striated muscles. The Z-discs, okay, well endowed with alpha-actinin. The Z-disc may also have some other proteins like vimentin. Okay, we will see that. Now, what we see is that in the case, okay, I'll show you. We don't have the Z-disc over here. However, we have some bodies in here, which, I mean, based on the proteins they contain by way of alpha-actinin, by way of vimentin, okay, it tells me that these guys which we are talking about here, which we call them dense bodies, these are called dense bodies. They can be likened to the Z-disc that we found in striated muscle fibers. Yes. So dense bodies, I mean, in this case, because they are performing almost the same function, so to speak, I mean, we can say they are analogous. Okay, so that's what we see. Now, again, in the plasma membrane, we see something. We see some invaginations in here. Okay, all these guys over here, which we call them vacuoli, caveoli. Okay, caveoli. My friends, these caveoli continuous with the plasma membrane, okay, they are in close relation with the, sarcoplasmic reticulum. In other words, these guys can be likened to, like the cisternae. Okay, so there will be areas, these areas will be well endowed with, of course, calcium ions. So they will release the calcium ions. Okay, good. Now, one thing is that in the, cytoplasm, in this case, sarcoplasm, what we will see is that there will be those kind of, especially actin, there will be other intermediate filament also. Okay. So that is how we are going to see it. Of course, we see a lot of dense bodies around. Okay, so these guys, they represent what we call the dense bodies, where I can see all these filaments. It could be intermediate filaments, and more importantly, as far as the contraction of this smooth muscle is concerned, they are actin filaments. Is it only actin filament in there? No. You also have myosin filament in there. But those ones which are attached to the dense bodies, they are the actin filaments. And that is why, because we saw that actin filaments were attached to the Z disc, that's why we are saying that the dense bodies, they are comparable to them. Now, the first thing that happens, okay, in the case of what we call this smooth muscle contraction, is that calcium ions, yes, will be released. From where? From especially the caveoli, okay, talking about the sarcoplasmic, this kind of reticular complex that we are having over here. Okay, that I want to put that one down. So calcium ions released from the caveoli, or you can say sarcoplasmic reticulum. Okay, once we release them, okay, and they come in here, the first thing is that calcium. There will also be another protein in this sarcoplasm, and that protein is an important protein which we are talking about. We call it calmodulin. Now, the name calmodulin is calcium modulating protein. That's the full name, actually, calmodulin, calcium modulating protein. Now, what it means is that in smooth muscle contraction, an important protein, the first protein, which is very important for interacting with calcium, this time calcium is not troponin, it's not going to interact with troponin. Rather, the one who is going to regulate it is who? Calmodulin. So calcium will bind to it. And what do you think we get? We get a complex made up of what? Calcium and calmodulin, which we call it calcium calmodulin complex. That's the first complex we want to form. Once we form this complex, one useful thing that I want you to be aware is that I told you that the myosin hairs, in the case of the smooth muscle, they don't have ATPase activity. Therefore, there should be a molecule, or there should be an enzyme for hydrolyzing this ATP molecule for us. Yes. Okay? Yes. And my friends, that molecule will be activated. That molecule is something we call Now, there's a concept I want to put across here. If you look at the myosin molecule, it's having two chains. At the molecular level, myosin is having two chains. It's having a light chain and it's having a heavy chain. My friends, I want you to concentrate on a light chain. Yes. Now, if I can deal with something light and produce an effect, why do I worry myself with a heavy one? Okay, make things easier. So we are interested in the light chain of myosin. Yes. And that is the area which has to be phosphorylated. Yes, that is the area which has to be phosphorylated for this, reorientation, re-energization, okay, of what we call the the myosin. And so the enzyme which is going to phosphorylate the myosin light chain is what we call myosin light chain kinase. But initially it was inactive. It was inactive. Yes, that's what I want you to know. It was inactive. Now its activation is going to come from, of course, this calcium calmodulin complex. So that upon activating the myosin light chain kinase, you've done some biochemistry, and you know that some enzyme class, okay, referred to as kinases, what they do is that they phosphorylate. They phosphorylate, yes. And by phosphorylating, kinases use ATP molecules. It means that this myosin light chain kinase is going to phosphorylate. It's going to hydrolyze what we call ATP molecules so that we get ADP and inorganic phosphate. The inorganic phosphate is the one who is going to phosphorylate. We're going to use it to phosphorylate who? Who are you talking about? Myosin light chain. As simple as that. Yes. And once this myosin light chain gets phosphorylated, okay, then the next thing that we will see is that this gets activated. Then we are saying that it's going to phosphorylate. So it will phosphorylate myosin light chain. Myosin light chain. Now this guy is myosin light chain kinase. The kinase is going to phosphorylate myosin light chain. And once myosin light chain gets phosphorylated, that's the only thing that we need. We get that energy to drive the whole process. Okay? And so what is going to happen? It is going to, of course, now get reoriented. Okay? Or it's going to undergo some kind of conformational change. Okay? And of course, it's going to be re-energized. Re-energized to do what? So that it can interact with, of course, the actin filament. This is as simple as that. Okay? So then the question is this. This time around, we are saying that the hairs, they are not going to feel the ATP molecule. They don't have anything to do with them. So it's not ATP molecule who is going to interact with, of course, the myosin hairs so that it causes that dislodgement of the myosin hairs from, of course, the actin. No. It's not going to be that one. But rather, in every situation, what I believe is that there should be a way out. Okay? So, everyone's case is different. And for the way out of this, smooth muscle contraction, once it is there, then one thing that we need is that this myosin light chain, which we said there was a kinase to phosphorylate it, there's also a phosphatase. Yes, we also have myosin phosphatase. So that what is going to happen is going to, of course, dephosphorylate. It's going to dephosphorylate, of course, this, phosphate group from, of course, the myosin light chain. And that is as simple as that. Again, just like rigor mortis, if, sometimes the dephosphatase is not able to work, so well, okay, and sometimes, especially, after death, if it's happening and it's after death, that's what's going to happen. We call it latch state. Latch. So in striated muscle, we talked about rigor mortis. In smooth muscle, that state of rigor mortis, because of deficiency of that enzyme, that dephosphatase, is what we call the latch phase. Okay, so that is one thing that I want you to know. So that is with the muscle contraction that I want you to be aware of. Now, having seen this, then the next thing that we want to see is to look at types of muscle contraction. Now, we looked at the mechanism, how it's going to take place. So we want to quickly talk about types of muscle contraction. Types of muscle contraction. Now, importantly, there are two main kinds of muscle contraction. Yes, there are two main kinds of muscle contraction. And what are these two main kinds we are talking about? We have something we call isotonic muscle contraction. Isotonic. Now, this time around, whenever we talk about tonicity, yes, we are not talking about concentration here. Tonicity in this sense has to do with the force, the effort we are applying to overcome the load. Isotonic contraction. And then we also have isometric contraction. My friends, whenever we say metric, it has to do with measurements. In this case, the measurement we are interested in is the length of that muscle. Yes, that's what we are talking about. So isotonic. Now we are talking about force and we are talking about length. Now always one will be generated and it gets to a stationary level. It gets constant. Yes, while the other parts will be changing. What do I mean by that? In case of isotonic contraction, you will begin generating the force. Then it gets to a point so that it becomes stable. So isotonic, the force remaining constant, but the length changing. Then in the case of isometric, iso has to do the same. Metric, the same length. Initially the length will be changed, it gets to a stationary level. Okay, and of course we'll be generating, the force will be what? Changing. So now, one thing I want you to be aware is that in isotonic contraction, we have two kinds. There are two kinds of isotonic contraction. And the first one is called concentric contraction, and we also have eccentric contraction. Yes, this is what we are going to look at. Now, the most important one that I want you to be aware is that this principle I always tell people that generally, whenever muscles contract, they cause movement. Yes. And by causing movement, the muscle fiber will be shortening. Okay, so if you can see, this is my biceps brachii. Okay, upon contraction, what do you see? See that the fiber length, okay, will be shortening. Now, if I have a situation, assuming there's the load in my hand, if I have this situation and I want to raise this load, okay, so raising the load, what do we see? The force that I'm not using maximum force because this load, okay, is way lower compared to the force or the effort I'm applying. I can apply that. I'm not applying my maximum effort because it's a small thing, I can carry it, I can raise it. So using, of course, for me to raise it this way, then I have to cause flexion at my elbow joint. The muscle is going to contract, and which muscle is contracting mainly? We are looking at, of course, the biceps brachii muscle. So, of course, I've raised it. So what have I done? In situations where, of course, the load is far lower compared to that of the effort you can maximally apply, I'm applying minimum effort. For this reason, this one becomes an example of concentric, muscle contraction. Why? Because the efforts, even the minimum effort I applied, has been able to overcome the load. So that, of course, the muscle fibers, okay, they've shortened. So the force is just the same, because I'm not applying another force again. Just the minimum force I'm applying, but I'm able to overcome the load, to cause flexion, to cause the muscle fibers, okay, to shorten. So that is an example. So this guy over here, so in concentric, muscle contraction, the key thing that we want to put across here is that the muscle fiber will shorten. The shortening of the muscle fiber, and that is the classic muscle contraction we want to see. Yes. Now the opposite one, what we see is that there could be situations where, yes, there's a load. I want to take it. Or let's say they gave me the load, then immediately the load was too, even the maximum effort by way of force that I will apply, I'm still unable to, bring it up. In other words, this prime mover by way of the biceps will elongate. Instead of, contracting and shortening, it rather elongates. Yes, so in situations where the load is greater than the maximum effort you can ever apply, then it means that, it rather cause elongation of the muscle. So in eccentric contraction, the load is far greater than the maximum effort you can apply. Therefore, the muscle is going to what? Gets elongated. You have applied the maximum effort, now it's constant, you can't do anything again. But still, you are not able to hold on to it because the weight of the load is heavier. Okay, so in this case, the muscle elongates. Okay, that is what we are seeing. Now, in both cases, some kind of movement has taken place. We've covered some kind of distance. It means work has been done. Now, when you are at a senior high school, junior high school, you learned that work is done when force moves a load over a distance. Okay, so once you've covered a certain distance, whether it's a shortening or it's extending, there has been some work. But the work we've produced, they are different. Now, in the case of this one, because I was able to move the load to cover a positive distance, that was my desired, okay, so that I can flex it. This one becomes a positive force. Force times an acceleration. We've accelerated to get it. Okay, the force, an acceleration. Forces, you talk about the mass times acceleration. Once I'm able to move it to the desired level, that's an acceleration. So force times that distance, and it's a positive distance I've covered. Unlike in the case of eccentric, which we've covered a negative distance, that's not the desired distance I want to go. I want to rather come this way. So it becomes a negative work. Okay, a negative distance we've covered because there's going to be deceleration. Then in the case of isometric contraction, what are we saying? Now there are situations. For instance, you want to push against a stationary, object. Okay, and of course, what we are saying is that your force will be increased. You want to try. You are trying. You are pushing against it. You are still pushing. The length is remaining the same, but you are generating more force trying to overcome the load. Or in situations where, of course, the load is just the same as the maximum effort you can apply. It means that the object is neither coming to your desired level, so that the fibers of the muscle will reduce, will shorten. Neither is it going down so that there is elongation. The fibers will remain at the stationary, but you are generating more force so that you can keep it at that point. Such type of contraction, we call it isometric. Force is generated. There's increasing force, but the length remains the same. So you see that the belly of that muscle will be getting bigger and bigger with time, but the length will remain the same. That is isometric contraction. In such a situation, no work has been done. You've not covered any distance, so no work has been done. Okay, so these are the two main kinds of muscle contractions. Now, having told you about this, then I have to be quick and tell you something. Now, the stress we are putting on these muscle fibers, they are very great. The stress that we are putting on them, that is why these muscles, they will have to respond to that stress. Yes. Okay, now assuming it's getting to an exam and you got a lot of things to cover, it means that the number of hours you spend, when you will sleep will be shortened. It means you are putting stress on the body. So in the same way, if you are putting more stress on these muscles, the muscles will also adjust. By you the same way adjusting to learn more, that is what we are doing. And so I want to explain one important concept for you, that the adaptation, there's some kind of adaptation by these muscles to the stress you are putting on them. So adaptation of the muscle cell, adaptation. And the adaptations we want to talk about, the first one is what we call hypertrophy. Hypertrophy. First one is hypertrophy. Okay, hypertrophy. The word hyper has to do with increase, and trophy has to do with the size. The size becoming larger. Like trophy, hypertrophy, becoming larger. So what we see over here is that in hypertrophy, especially with, of course, striated muscles. Yes, striated muscles. By way of cardiac muscles. So for instance, if there are a lot of, the heart will have to really pump blood to go through some occluded vessels where there are plaques, okay, where there are arterioma, that has to really work very hard. It means that with time, the cardiac muscle fibers will enlarge. That is hypertrophy. And evidently, we see that the heart will become enlarged. Okay, some people call cardiomegaly. Then, these muscles, sometimes you raise them, skeletal muscles, they become larger and larger. Okay, in such a situation, skeletal muscles they can undergo this kind of hypertrophy. That's one way, because you impose a lot of stress on it. Now the next one is that, especially for the smooth muscles. Now my friends, smooth muscles can also undergo hypertrophy. Yes. For instance, if you look at the smooth muscles in the uterus, okay, when one gets pregnant, one thing that is going to happen is that there's going to be some hypertrophy. They are going to enlarge. But most importantly, for smooth muscles, they will undergo something called hyperplasia. Hyperplasia. Okay, hyperplasia. So it means they are going to proliferate, they are going to undergo mitotic division, generating a lot of them, so that they can bear the stress. Smooth muscles. Okay? Now the same way, if the muscles they can enlarge, then it means that, in situations that you are not giving them that stress, okay, or let me say you've taken away something, then it means they are going to decrease in size. For instance, if someone stops raising metal dumbbells and what have you, then what do we see? With time, these developed muscles, they tend to, undergo some kind of, evolution, so to speak. In this case, we call it atrophy. 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 Okay, decreasing in size because of minimal, use of it. You're not putting a lot of stress on it. But there's something to metaplasia. That is one important thing that I want to tell you. There's also something called metaplasia. Now, metaplasia, most often we see them more with epithelial tissues. For instance, if someone has something we call GERD, gastroesophageal reflux disease, talking about that kind of heartburns, so that something happens, it becomes so chronic, there's some kind of transformation of the stratified at the lower region of the esophagus, which that's supposed to be stratified squamous, non-keratinized epithelium, changing to become, of course, simple columnar epithelium, having some goblet cells in there. So that because every time there's that kind of acid reflux, it can deal with that stress. Okay? The muscle too shows some kind of metaplasia. So if you are using it for something which the bone is the one we're supposed to do, putting a lot of stress on it, sometimes these muscle fibers, they may change to become bony. Yes. Typical example, the name we call it myositis ossificans. After the muscle has been inflamed, because you put a lot of stress over there, it's going to transform to become bone. I mean, whenever you see ossification, okay, it becomes bony. Okay, so these are the ways that, I mean, the muscle will respond to, of course, stress, the adaptation that I want you to be aware of. Now, the next thing that you want to look at is that generally, there's one more concept I want to tell you. Generally, muscles who are tied to bones, yes. Muscles via tendon, they are going to attach to bones for skeletal muscles. But there are some muscles, they don't attach to bones. No, they don't attach to bones. They are tied to subcutaneous tissue. And by attaching to subcutaneous tissue, such muscles, we call them Paniculus, carnosus muscles. Paniculus, carnosus muscles. I want you to be aware of these muscles too. The general skeletal muscles are going to attach to bones, but there are some kind of muscles, or let me say muscles are, they're supposed to have some bony attachment. But these ones, they are not attached to bones, no. They are rather, attached to subcutaneous tissue, and we call them, Paniculus carnosus. The word Paniculus has to do with subcutaneous tissue. Okay, now, importantly, I want you to know these guys. There's one muscle I want to show you. Now, there's this muscle in the neck, which upon contraction causes wrinkling over here. It's a flat muscle. For that reason, we call it platysma muscle. Platysma. Platysma muscle. Well, not only that, there's this muscle over here. Now, this area where the thumb is, this bump we have over here, okay, we call it pinna eminence. There are some muscles which contribute to it. We will get to know them. This area where the pinky base of the little finger, we call the hypothenar muscle. Hypothenar muscle. Now, in the region of the hypothenar muscle, there's one muscle that's attached to bone. And that muscle, we call it palmaris brevis. Now, I'm going to show you the nomenclature. I'll teach you the nomenclature before we end this class. And we understand that whenever we hear the word brevis, now palmar because it's in the palm, brevis word has to be short. I mean, the opposite of short will be long. So we see that, okay, based on this kind of size we talk about. Now, not only that one, there's one muscle, although I want to tell you that that one will have smooth muscle fibers. That one we call it dartos muscle, dartos. And this dartos in males, yes, may cause wrinkling in there. Some of the facial muscles, yes, may also be Paniculus carnosus muscles. Now, why am I interested in telling you this? Because the next thing I want to tell you is about, some important things that we have to know about muscles. One of them is attachment of muscles. So the first point, some key concept that I want you to be aware of. The first one is muscle attachment. Attachment of muscles. Now, it's saying that these skeletal muscles, they are going to attach to bones. So attachment of muscles. Muscle attachment. Now, muscles will have two areas of attachment. Yes. They have an area where they originate, they come from. And they have an area where they're going to reside eventually. They are going to insert. Yes. So muscles will have two kinds of attachment. One is called origin. Origin. And the other one is insertion. Now, whenever we say origin, that's where they are coming from. Now, if you are coming from somewhere, then it means that area should be very stable. Yes. In the Akan dialects, we say that is going back. So it means that it should have a stable origin. So that if anything, you can go there. So usually we say that the stable point of attachment is called the origin. While of course the movable, the less stable one, is called the insertion. Already, I've told you that whenever muscles contract, they cause movement. Yes. That's the first I want you to be aware of. Now, for instance, if you look at this friend of mine, what I see is that there's one muscle over here, just to use that one to explain something to you. There's one muscle, we call it supraspinatus. Supraspinatus muscle. The name is supraspinatus. Supraspinatus muscle. Now there's this spine over here. So this spine, above the spine, you become supraspinal fossa. So there's a muscle which originates in the supraspinal. That's why we are calling it supraspinatus, and the way of naming muscles based on their attachment. So the supraspinatus, it comes all the way. Now this is called humerus. At the proximal end of the humerus, there's something called greater tubercle of the humerus. So these muscle fibers will run all the way. They'll come and insert over here. So that is the origin, and this becomes the insertion, attachment. Origin is stable, insertion is movable. So that upon contraction of this muscle, then it's going to pull this muscle this way. So once you know the origin of the muscle, you know the insertion of the muscle, you know how the muscle fibers are oriented, then you know the action of that muscle. That when this muscle contracts, what is going to happen? For instance, this supraspinatus is going to cause, what have I done? This is called what? Abduction. Now abduction, I can even go this way. I can even go a bit more. So just starting abduction, that is called initiation of abduction. 0 to 15 degrees. We explain those things for you. Okay, so that is, origin and of course insertion. Now there are some people, they do rote learning. They don't learn about the precise origins of these muscles, the insertions of these muscles. They just memorize the actions of muscles. Completely wrong. So whenever I see someone doing that, I know the person doesn't know what he's doing. You have to know the origin, the insertion, by way of the attachment. And once I know that the point of origin is stable and the point of insertion is movable, whenever the muscle fibers contracts, the point of origin will be pulling the point of insertion towards itself. It's as simple as that. Now, sometimes there's something we call fixators. Say that at the point of insertion, which is supposed to be movable, it can be fixed. So that upon contraction, the fibers at the point of insertion rather be pulled the point of origin. That's also another case. Okay, so in special cases where we will fix the point of what we call it, insertion, we can pull the point of origin toward the point of insertion. That's also another point. Okay, that's good. So that's by way of the attachment. Now the other one is that we have something we call prime mover. Something we also call agonist. Now, if there's a particular desired movement that I want, there's a desired movement that I want. For instance, this muscle, okay, I'm looking at the upper limb. Everyone knows this muscle by way of the biceps brachii muscle. Okay, the biceps brachii muscle is the prime mover as far as causing flexion at the elbow joint is concerned. That's the prime mover. Okay, that is what we see. Now, this prime mover is the one we are also calling it agonist. Now, this prime mover, sometimes it may not work on its own. It may need additional support from other muscles to work. For that reason, another concept that comes in is what we call synergist. There's another important concept that I want to put across here, synergist. Synergist. Muscles working together to produce a movement. Now, if I cut this muscle, where the bicep brachii over here, if I cut it over here, then reflect it, there will be another muscle deep to it. We call it brachialis muscle. After all, you know that the arm is called brachium. Okay, so brachialis muscle. So once I cut the bicep brachii muscle and I reflect it, I will see brachialis muscle. And that brachialis muscle is also relevant in causing flexion at the elbow joint. Therefore, it becomes a synergistic muscle to bicep brachii muscle. There's one more concept I want to put across here, and that is something we call fixators. Fixators. There are some muscles. Now, these bones, they can move. Sometimes we need the bone to be a bit stable. So, for instance, for me to cause flexion at the elbow joint, this bone, okay, should be stable. And so it will be stabilized by way of the humerus getting a bit stability from this big muscle I have over here, which we call the deltoid muscle. Deltoid muscle. Okay, sometimes even we can have, some of the trapezius also doing some kind of stability with it, to it. Okay, that is one thing I want you to be aware of. Fixators. Now, having seen that, then we also have what we call antagonists. Antagonists. And the next thing I want to put across is antagonists. Now, you know protagonists, you know antagonists. The desired movement by way of the agonist helping me to do it. Now, if there's a desired movement, now what do I see? When this bicep brachii muscle is contracting, the opposite side, which is called triceps brachii, because having three origins, three hairs, we understand these terms. This one is rather relaxing, therefore it's causing elongation. While these muscle fibers are shortened, this one is rather elongating, relaxing. It is working against this, bicep brachii. If they were synergists, then as this one is contracted, this one will also be contracting. But at the opposite compartment, which is the posterior compartment of the arm, biceps in the anterior compartment of the arm, posterior compartment, triceps, is rather causing relaxation. For that reason, we say that this tricep muscle becomes antagonistic to who? To biceps brachii muscle. That's also a useful concept that I want you to be aware of. So it tells me that antagonists and agonists, or the prime movers, so to speak, will be at different compartments. Okay, so biceps anterior compartment of the arm, tricep posterior compartment of the arm. Now, if for instance, if I look at my hand, there's some intrinsic muscles in the, there's some extrinsic muscles in there. Okay, one of those muscles we call it, flexor. Okay, anything which will help me to flex at the wrist joint, flexor carpi ulnaris. I also have flexor carpi radialis. What are they? Both of them are flexors. So they work in synergy. The same way, if I go back, I have what we call extensor carpi ulnaris. Then I also have extensor carpi radialis longus and brevis. Whichever way. Once they are extensors, whether it's radialis or ulnaris, it means that they will help in extension. But my friends, these guys are also, they are working in synergy, either causing flexion by way of flexor carpi ulnaris, okay, flexor carpi radialis, or causing what? These guys are going to be, what are they going to be? They are going to antagonistic by way of extensor carpi ulnaris and of course extensor carpi radialis longus and brevis. Okay, they will be antagonistic to their flexors. But my friend, there's a catch. Because what happens is that because they are located at the ends, okay, lateral most aspects of the hand, then what we see is that they can also work in synergy. So if I do this, what have I done? I have I've moved my wrist joint, my hand at the wrist joint towards where I have the little finger, which is related to the ulna. This is called ulnar deviation. Ulnar deviation. Okay, something you can also call abduction. Okay, so and then the opposite side. Okay, this is called adduction. Bringing it a bit closer to the midline. Ulnar deviation. Then taking it away this way, so that this time around it is at the at the radial aspect. This one becomes, of course, radial deviation. Something because it's related to the thumb, we can also call it, abduction away from the midline. Okay, so these are some important points that I want you to know. There's another point I want you to be aware of. We have something we call intrinsic and extrinsic muscles. Intrinsic. Now, if it is intrinsic, then it is within. So I can have intrinsic muscles of the tongue. And when we say these intrinsic and extrinsic things, it is based on the attachment. If you are having both the origin and insertion in this organ of interest, then we are talking about intrinsic muscle. But if you are having one of the attachments in the organ of interest and another elsewhere, then it becomes extrinsic muscle. For instance, typically, I want to show you this. Okay, now look at this. This is the larynx. Now in the wall of the larynx, I see some kind of skeleton by way of the, what we call the thyroid cartilage. I also see the cricoid cartilage, okay, Hallin cartilages. What I see is that there's this muscle. We are still in the, larynx. There's this muscle between, of course, the thyroid cartilage and the cricoid. So there will be a muscle which we would name it based on the attachment, which we say cricothyroid muscle, cricothyroid muscle. Okay, it becomes an intrinsic because it's within the larynx itself. But what do I see? This hyoid bone is not part of the laryngeal skeleton. The thyroid cartilage is part of the laryngeal skeleton, and for that reason, this muscle, which we are calling it the thyrohyoid muscle, will be an extrinsic muscle to, of course, the larynx. Okay, that is one useful thing that I want you to be aware of. Now, if you've seen this, the next thing that I want to quickly, review for you is for us to look at the nomenclature of muscles. Okay, nomenclature. How do we, name muscles? Nomenclature of muscles. We want to see some important aspects, and then we will end with the types of skeletal muscle fibers, okay, for today's meeting. So, nomenclature of muscles. How we name muscles. Now we have about 700 muscles, a lot of muscles. So sometimes you don't always have to cram them. There should be some kind of clues to help you learn some of these things. Before I go to the nomenclature, there's some important thing that I want you to know. Arrangement of the muscle fibers. Arrangement of the muscle fibers. So, for instance, we can have one point where we arrange the muscle fibers in a parallel manner. Parallel muscle fibers. How do we see them? Now, if you look at this muscle, if you take a closer look, you can see that the fibers are running parallel to each, in this case, one another. Bicep brachii muscle. You get what I'm trying to say? So in this case, parallel. There are some issues you may have. Let me just show you this one too. A lot of muscles, they show this kind of parallel arrangement. Okay, like this muscle. Okay, parallel arrangement. We call it sartorius muscle. And my friends, whenever I mention sartorius muscle, I have to be quick and tell you sartorius. Sartorius. Sometimes we also call it the talus muscle. We also call it the honeymoon muscle. I'll explain all these things for you. Now, this sartorius, my friend, is the longest muscle we have in the human body. The longest muscle we have in the human body. Sartorius. Okay. Sometimes too, you may have the same parallel arrangement, but they will be intersected with some bands. Okay, so with fibrous bands, or let me say fibrous intersections. And there's this classic muscle that we find. Sometimes, these bodybuilders and all these athletes, they are able to, have well-developed muscles in their belly region. Okay, well-developed muscles in their belly region. And that muscle that you have, where you see that, we talk about this kind of six packs. Okay, that muscle, we call it rectus abdominis muscle. The six packs are coming from that kind of, intersection that we see. Rectus abdominis. Rectus abdominis. Rectus abdominis muscle. Now, you may have this kind of convergent fibers too. Convergent. Said that you may have this muscle having a very broad origin. There's this muscle over here. I can show you some portion here. Okay, in your pectoral region, your chest region, which forms what we call the bed of the breast. The bed where the breast is going to lie on. That muscle, this big muscle, we call it pectoralis major muscle. It has this vast origin, all the way from something we call coracoid process. Sorry, acromial process, okay, not coracoid process. Coracoid process is over here. It doesn't give attachment, okay, to, of course, pectoralis major. So I'm talking about acromial process. Then I'm also talking about, what we call the clavicle, okay, having a very vast origin. But my friends, the important thing is that it is also having under attachment, okay, apart from the clavicle, also to, of course, the sternum, these corsal cartilages, okay, and they will be coming all the way this way, spiraling to insert over here something we call the lateral lip of the bicipital groove, lateral lip of the bicipital. So all these muscles, they are spiraling to come here, converging at a point. So a typical example I want to give over here is, of course, the pectoralis major. Okay, pectoralis major muscle. Now, some muscle fibers, we describe them as being unipinnate, based on pinnation. So we say unipinnate. Unipinnate. Now, I'm sure you know about this kind of feather, or for instance, the fowl. Okay, if you take the feather, if you just take one half of that feather, that is how the muscle fibers are, unipinnate. That's some important muscle which will help me, okay, to bring these ligates closer together. Okay, we call them palmar interosseous muscles. So typical examples, you will see them palmar interosseous. Okay, they will be, of course, unipinnate. We will see a lot of them as we go back. I just want to tell you these ones. Yes, you may also have what you call bipinnate. And bipinnate is just like a feather. So if you take one feather, how it looks like, that's how the muscle fibers, they appear. Let me quickly show you something. There's one muscle we find over here. Take a closer look over here. This muscle, we call it rectus. Rectus femoris is straight. So you say rectus, and it's in the femur. So rectus femoris. Can you see how the fibers are? It's like a feather. Okay. So rectus femoris, for instance. Not only rectus femoris, but in this case, just like I had palmar interosseous muscles, we also have something called dorsal interosseous. You see them. They are also examples of dorsal interosseous. Now, if you have unipinnate, bipinnate, then you can also have multipinnate. Okay, multipinnate muscle. And multipinnate muscle, the typical example I want to put down is what we call the middle fibers of deltoid. Middle fibers of deltoid. My friend, it's not just deltoid muscle, middle fibers of deltoid. And the reason is that if you look at the deltoid muscle, it's going to have anterior fibers. Now, this one you see over here, this is called the anterior fibers of deltoid. And my friend, anterior fibers, okay, they are unipinnate. Again, you also have what you call posterior fibers. They are also unipinnate. But in the case of the middle fibers, we have several ones, okay, branching differently. So it becomes bipinnate. The middle fibers of deltoid is, of course, bipinnate. Now, one more thing that I want you to be aware is that some of these muscles, they have this kind of circular orientation, circular. So what we say is orbicularis. Circular orientation, circular. And typical examples, we are talking about orbicularis. And whenever I'm talking about orbicularis, the important thing that I want you to be aware of is this guy. Now, you see, with the eye, there's this muscle which goes around. in this circular manner. So this one related to the eye. Ocular has to do with the eye. So we talk about orbicularis oculi. Similarly, there's another one with the lip. Okay, it goes all around here. And this one is what we call, because related to the lip, then we want to use, oris has to do with the lip. So we talk about orbicularis oculi muscle. And also I'm talking about orbicularis oris muscle. Okay, these are some important things that I want you to be aware of. Now, we can now go to, of course, our nomenclature. So sometimes we may name some muscles based on size. Okay, based on size. And so when I'm talking about size already, I've told you that the longest muscle that we have is what we call sartorial. So based on size. So in terms of size, what am I talking about? I can talk about with respect to length. And I told you that we have some muscles which is very long. Okay, so let me start with that one. So I can have long muscle. So the fibers are very long. And we may talk about something like palmaris longus. Now, some of them may also be short. And what we use for short is brevis. So I can have longus, I can have brevis. So for instance, palmaris brevis. We have a lot of these guys around. Now, in terms of how flamboyant the whole thing is, yes, let me say that. How flamboyant the whole, that's also in terms of size. Okay, then I'm talking about how large is it. So we can have what we call magnus. Let me use maximus. Okay, maximus. So sometimes you may have something like major. For instance, it could be major for, I talked about pectoralis major over here. When I remove it, deep to it, I have pectoralis minor. Okay, these are the things, major, minor, with respect to size. Then maximus is also very large. Now remember that the largest muscle that we have in the human body is called gluteus maximus. So one other way of classifying these muscles is also based on where? Based on location. So for instance, maximus, by way of for instance, gluteus maximus, because it's located in the gluteal region. Gluteal, the area you sit on. Gluteus maximus, for instance. Well, it means that I can also have minimus or minor. Like pectoralis minor. This one I'm talking about minimus. So we also have pectoralis, gluteus minimus. Okay, so gluteus, this time we're talking about minimus. Now, whenever I talk about gluteus maximus, it reminds me of something. Some people, because they know it's the largest muscle that we are having over there, we think those kind of intramuscular injections, that's where we are putting it. No, that's not the place. We are rather putting it in the intermediate one, another muscle that we have over here, intermediate between them, so we call it intermedius. So we also have gluteus intermedius. Okay. Now, there could be another situation which we may nomenclate muscles with respect to their relative position or with respect to their closeness to the midline of the body. Yes. So, for instance, there's this muscle which will help you in escalation movement, side to side movement when you are chewing. You call them pterygoid muscles. Pterygoid. So, in terms of respect to the midline. So it could be medial, may have a muscle with medial or lateral. So I can have something called medial pterygoid. You will see them. I may have lateral pterygoid. Respect to the midline. The same way, there is this muscle over here. We have vastus. Now, in Latin, we don't say, with respect to size again, we may have something called vastus. Now, say vastus. Vastus. I'm interested in vastus. Okay, so we may say vastus. Or some say vastus. Well, very vast is big. It could be lateralis. It's towards the lateral aspect. Okay, so this way, little, toe is here. So this muscle is called vastus lateralis, and I may also have vastus medialis. Now, when I reflect this muscle over here, rectus femoris, deep to it, I also have vastus intermedius. Yes, that's also another thing that we will look at. So with respect to that kind of midline that we are talking about. So with respect to location, I've told you, gluteal region, pectoral region, okay? Also, we can name them with respect to their attachments or where it is located in terms of location again. There's this muscle which upon contraction, can you see the wrinkling over there? That muscle is called frontalis muscle, frontalis muscle. The opposite muscle, we call it occipitalis muscle. There's a common, aponeurosis over there, we call it epicranial aponeurosis or gallia aponeurotica connecting the two. So this muscle together, we call it occipitofrontalis muscle. Okay, that is another useful term. Now, also we can name muscles based on the number of hairs. The number of hairs. Okay, based on number of hairs. And whenever we say number of hairs, we are talking about number of origins. And importantly, we can talk about that one. We can name them based on number of bellies. Now, for the number of hairs, we may have something called biceps. Now, I've told you about biceps. For example, bicep brachii. Why are we calling it biceps? Because having two origins. One origin from this guy, what you call it, that shape of cranial process. Okay, that's where the short head is coming from. And there's also a long head coming from what we call the supraglenoid tubercle. So two origins, two hairs, ceph, biceps. Then you may have triceps, the one over here, because having three origins. Okay, having one origin from, of course, the long head coming from, of course, the infraglenoid tubercle down here, and the origin by way of the lateral head, which will be coming. Okay, there's this spiral groove. Okay, above the spiral groove, laterally, lateral head will be coming right below the spiral groove. The largest head being the medial head also originate there. They also have quadriceps. Quadriceps. So we have triceps, quadriceps. It means that you are having four hairs and for that matter four origins. The typical one I showed you is what we call the quadriceps femoris, related to the femur. Okay, femoris. So why? Because it's made up of one point where it's called vastus lateralis, vastus medialis, rectus femoris, and of course vastus intermedius. Four, all of them having a common tendon, the quadriceps tendon, to exert the mechanical force, okay, through of course this patellar tendon, to of course the tibial tuberosity. Okay, so that is one thing that we want to be aware of. We can also name these things based on number of bellies. Number of bellies. And we can even name based on attachments. An attachment, I'm talking about origin and insertion. Okay, the belly, there's this muscle over here, we call it the digastric muscle. Okay, from here, then it comes this way, we call it digastric muscle. Why? Because it's having two bellies. Now, the word gastric has to do with the stomach. And people, usually confuse the belly to be the stomach. Okay, well, one important organ in there, in the belly region, is of course the stomach. So it doesn't matter. So digastric muscle, having two bellies. Okay, good. Now, how it resembles something, we can also use it to nomenclate them. For instance, there's this muscle, we call it gastrocnemius. Okay, having some kind of bellies like the stomach. So we're having two bellies. Okay, it's having, one of them being the lateral one, resembles the stomach, another one. So we have the medial head of gastrocnemius, lateral head of gastrocnemius, the one which we see it in the calf region, okay, very prominent in some athletes, some individuals. Okay, so that is, I mean, one thing that I want you to be aware of. So these are some useful muscles that I want you to be aware of. Okay, so I've mentioned origin and insertion. Okay, there could be a muscle that I'll talk about. Good. There's this muscle we find over here, and you can see it here. There's this muscle we call it sternocleidomastoid. Sternocleidomastoid muscle. Sternocleidomastoid. Now the name is sternocleidomastoid. Now it's based on the attachment, the origin and insertion, because it's having one of the origins, okay, from where we have the sternum, the clavicle, cleido, and I'm going to insert all the way to this guy over here, where is the mastoid process of the temporal bone. So the name is sternocleidomastoid muscle. Yes. You may have some muscles named based on their action, the sort of action they are performing. Action. For instance, you may have something you call abductor pollicis. Okay, abductor pollicis longus. For instance, abductor pollicis longus. Anything pollicis has to do with the thumb. Hallucis has to do with the toe, the great toe. Okay, so abductor causing abduction away. Flexor. Okay, extensor. So if you see, here some names: flexor, pollicis brevis. Okay, these are the things: extensor pollicis longus and what have you. Adductor pollicis. These are some names that you may hear based on the action they are performing. Either it's a flexor, it's an extensor. Okay, these are the things we are talking about. For now, before I will forget about it, let me tell you. We've seen that the longest muscle is called sartorius. The largest muscle is called gluteus maximus muscle. How about the smallest muscle? It's found in the middle here. We call it stapedius muscle. Stapedius muscle. And there's one more muscle that I want you to be aware of. The muscle, although it's belly. And whenever I say belly, I'm talking about the fleshy component. And then to attach the bone, it will have a tendon. So the muscle with a very small belly, but having the longest tendon, which is often confused as a nerve by some individuals who have not been to the gross lab, for instance, before. So the freshest. For this reason, this muscle, colloquially, we call it the freshest muscle, freshman's muscle. Okay, so we call that muscle that muscle is called plantaris muscle. Plantaris. Okay, the muscle with the longest plantaris muscle, the muscle with the longest tendon. Okay, that is what we are talking about. Okay, now we have several muscles. Based on whether it is more internal. For instance, you may have something you call obturator internus. Obturator internus. Obturator internus. There's this muscle which will be in here. We call it obturator internus. Because there's this, area which there's a foramen over here. We call it obturator foramen, which will be bridged, okay, by this membrane, which we call obturator membrane, leaving a small obturator canal above here for some obturator neurovascular structures to pass over here. So if you are a muscle, you are attaching to the inner portion, then we call it obturator internus. If you are coming externally, we call it obturator externus. Now, based on the shape again, there's this muscle I want to make mention of. There's this muscle where it's pear-shaped, coming through the greater sciatic foramen. We call it the piriformis muscle. That's why I call it piriformis muscle. Okay, so these are some ways that we will nomenclate some of these things. There is also a way that we nomenclate some muscles, okay, based on the structure. What is the constituent? There's this muscle we call it semimembranosus. Okay, then we also have semi-tendinosus. Semi-half, partially. So it is partially membranous. Partially having, of course, this kind of muscle fibers. And then this one is semi-tendinosus, tendinous. So I have this muscle with a very long tendon. So we call it what? Semi-tendinosus muscle. Okay, semi-tendinosus. Then you may also have what? Semi-membranosus, muscle. Okay, semi-tendinosus, it got to be at the lateral aspect. Okay, so a semi-tendinosus muscle, very long tendon, and then it's lying on the belly of that muscle where it's half membrane, half muscle. Okay, semi-membranosus muscle, based on, of course, the structure. That's what we are talking about. Now, even based on how the muscle fibers are oriented, you may have some of these muscles. You may have some muscles which are straight muscles. We call them rectile muscles. So they will end with the word rectus. Sometimes the muscles may be circular. I've told you about orbicularis. Some of them may be oblique. So obliquus, or oblique muscles. And then some of them may be running transverse. So we may say transversus. For instance, we will see that there will be the one I've mentioned already. Okay, rectus abdomen, straight muscle of the abdomen. Can talk about orbicularis oris. Okay, circular fashion. You may have what? The oblique muscles, external oblique muscle, internal oblique muscle. Okay, these are the things. Now, I don't need to forget about, for instance, these intrinsic muscles, some of these intrinsic muscles of the thorax. Okay, talking about internal intercostal. It's more internal, it's in between the ribs. You know, the word costal has to do with the rib. So the muscle find attachment, okay, more closer in there. So internal intercostal, external more outside, intermediate. Okay, so these are what we are, or the innermost, okay, going more in there. Then transversus, running transversely. So for instance, we have transversus abdominis muscle, transversus thoracis muscle. Okay, so these are some of the things, okay, that I want you to, of course, be aware of. Now, as we move on, there will be other things that we will talk about. Okay, they will come. I will be explaining all these ones for you. But the last thing I want you to be aware is that in skeletal muscle fibers, we have 3 kinds of skeletal muscle fibers. And it is based on how they twitch. Okay, either they twitch fast or they become fatigued. You know, they are highly resistant to fatigue. Okay, so that is the last thing that we will do for today. And then, of course, we will continue the next time. Skeletal muscle fibers. So we have 3 kinds of the skeletal muscle fiber. 3 kinds. Three kinds of the skeletal muscle fibers. Let me even tell you, there's this muscle, for instance, is in the pupil. So we say, because it causes dilation of the pupil, based on action, so we call it dilator pupillae. You may also have sphincter pupillae. Okay. Now, before I go on with this, there's one thing that, in case of cardiac muscle fibers, you know that the main muscle fiber is going to be in the middle tunic. Now you get to know, the heart is a hollow organ. Blood will be in there, so it's a hollow organ. Some of the time, blood vessels, they are tubular. Once there's a tube in there, then you are having tunics, coats. Now, generally, the middle tunic for these tubular organs is the muscle tunic. For the heart, it's going to have what we call the myocardium. So cardiac muscle fibers will be in there. Okay? But in the case, okay, now you know from endocardium we are going to myocardium, okay, and then from myocardium we get what? Epicardium. The epicardium, which we can liken it to something we call the epimysium of course the skeletal muscle. Okay, that's something I mean we've looked at. In the case of the smooth muscle, most of these tubular organs, okay, internal organs, they are going to have what we call smooth muscle fibers. The inner bladder. But the inner bladder, importantly, the smooth muscle over there, there's a name for it, which I want you to be aware of. We call the detrusor muscle. It's a special name, detrusor. Smooth muscle fiber in the urinary bladder, we call it detrusor muscle. It's the one which will take in at the neck of the urinary bladder to form something we call the internal urethral sphincter. You are aware that the external urethral sphincter is made of skeletal muscle fiber, but this detrusor muscle is made of smooth muscle fibers. There's one more thing I want you to be aware of. You know that in cold conditions, what happens is that we say that these hairs, what do? They contract. Sorry, these hairs, they become perpendicular, okay? They don't lie flat, they become perpendicular with respect to their skin surface. Why? Because of contraction of the associated muscle, which we call it erector pili muscle. Erector pili muscle. Now, erector means it is going to cause erection. Pili has to do with the hair. The hair which will cause, upon contraction, will cause erection of these kind of muscle fibers. Okay? That one you might think it is skeletal muscle. No. It is rather smooth muscle fibers that we have over here. I want you to really be aware of this. Okay? Good. And I've also mentioned the smooth muscles in the eye by way of the sphincter pupilli. Smooth muscle. So sphincter, it will cause meiosis. So it means that under which system? Under parasympathetic stimulation. Meiosis. Where, of course, there is bright light, meiosis will take place because of contraction of what we call sphincter or the constrictor pupilli muscle. Pupilli. Sphincter pupilli. Okay. Then, if there is danger, okay, under sympathetic stimulation, dark environment, dilated people will have to come in. Okay, dilated people. Okay, good. So that is, one thing that I want you to be aware of. Now, just to talk about the skeletal muscle fibers that I'm talking about, we will have what we call the type 1. They also have type 2, another type 2. But you have type 2A and you have type 2B, okay? Now the type 1, we describe it as slow oxidative. Now, you may call this one intermediate, having the intermediate fibers, okay? Or you can say slow or let me call it fast aerobic. And then this guy over here is, now this one, it is having a lot of myoglobin, is having a lot of mitochondria. For that reason, the type 1, we also call it red fibers. Now this one is also, because it's aerobic, there will be some red, but this one will be darker. Okay, dark red. This one will also be red, but this one will be darker. That's why you say it's intermediate. And then we also have the white fibers, okay, which are fast glycolytic. Okay, these are the white fibers. Now, one thing is that in a particular area, you may have combination of all these muscles. But the muscle which is very relevant in endurance, in posture, is the type 1. But it doesn't generate a lot of energy very fast because it has to go through oxidative phosphorylation. It's endowed a lot of mitochondria, endowed a lot of blood vessels, dark red. Okay, so mainly your back muscles, okay, of course, some in your neck, okay, most areas, okay, we are going to have a lot of these fibers. Now for the intermediate, it is mainly for standing. Okay, now for this one, because this one is slow oxidative, it doesn't easily get fatigued. Okay, and its velocity is not very fast, it goes slowly. Contractile velocity is not very fast. Therefore, this one resists fatigue, okay, very well compared to, of course, this type 2A, with the intermediate one. It's also red anyway, but that one is mainly for standing. So of course, your lower limb, especially those muscles in there, okay, they are going to have like soleus, like gastrocnemius, all those muscles, the thigh muscles, they are going to have a lot of these type A1. But one thing that we see is that the more you endure, you may convert these type A to become type 1. Okay, there will also be a lot of myoglobin because you've gone through that kind of endurance, a lot of exercise and what have you. You may have some of them transforming to become, you know, the type 1. But this guy over here, which we see them in some of these ocular muscles, like extraocular muscles of the eye, okay, levator palpebrae, superioris, okay, talk about, medial rectus, lateral rectus, a lot of these, ocular muscles, okay, they will be having some of these, mainly the type type 2B, white fibers. They undergo a lot of anaerobic glycolysis. And you know anaerobic glycolysis is going to produce a lot of lactic acid. Okay, so they are less resistant to fatigue. But their speed of contraction is very high. Okay, fewer myoglobin, of course, fewer blood vessels. That's why they will appear, you know, white. But by and large, what I'm trying to say is that every muscle everywhere, there will be, varying proportion of all these, fibers we are talking about. Ladies and gentlemen, I hope you find this helpful. This has been a marathon. Okay, I want you to understand all these concepts so that I can apply them, you know, accordingly. I'm very grateful for your time this evening. Have a good night, all of you, and may the good Lord richly bless you. Amen.